So today I'll talk about certain aspects of inertial impact on active matter. Uh, okay, so the people who are involved in this, I mean, this is a list of collaborators and students with whom I have been working for last decade or so. This work, part of this work is done by Chitrak. This work on active polymers and inertial impact on their properties. And Manish is in the audience. He also has a poster. A lot of the work is done by Manish, all the analytical calculation for uh, active particles in the ideal limit. And Shubhendu had done, was a postdoc. So he had done some calculations on the many body active Brownian particles and some emergent properties, steady state properties of that. And in that project, Fernando was a collaborator in that. Okay, so before I get into the inertial impact, let me just quickly summarize what typically we do in active matter. So some of the problems at least are like motivated by active colloids, genus particles which can use local energy, I mean utilize fuel locally and self-propel. Uh, but these particles are typically of extremely small mass and they have an inertial relaxation time which is very small, so hundreds of nanoseconds, with respect to the typical persistence time of these particles. And as a result, one can often neglect the inertial effect in those kind of systems. On the other hand, uh, if one takes bigger particles. For example, these vibrobots, some vibrated granular materials. So you vibrate this substrate on which, because of the frictional asymmetry or something, the particle can take locally the energy, and once it drops, it can slide and stick in one direction, slide in the other direction, and then as a result, it can move. So in all those systems, of course, there is inertia, and the inertial, the relaxation time, inertial time scale, that becomes significantly large and in certain cases can become comparable to the persistence time of the system. So whenever the persistence time and inertial time scales are comparable, we expect to see its impact on that. So, okay, so this could be one example. There could be examples of insects. There could be examples of, like, all these are active granular materials. There could be examples of larger animals, hex bugs, all those kind of systems in which inertia can influence their properties. So now I take a step back and look at this phenomenon of motility-induced phase separation, which today morning also people talked about, at least mentioned about. So in this overdamped systems, it was seen both in simulations and in experiments that if you have the systems driven at a high enough self-propulsion speed, so if all the active particles has high enough self-propulsion speed, these are active persistent movers, and has density which is beyond some critical density. So you can have this phase separation. So here particles repel each other, but they coagulate, they cluster together because of the self-propulsion fit and the repulsion between particles. So this is the motility-induced phase separation which was seen, which was observed for overdamped system. But what turns out is that if one increases inertia of the particles, individual particles in this system, one can go. So for example, this particular example of this vibrobots has an inertial time scale, which inertial relaxation time which is of the order of 0.1 second, whereas the persistence time is same order, 0.4 second. So in those kind of systems, you cannot really ignore the inertial effect, and so this was one result taken from this paper. They measured something called a delay function, and the delay function was what? That each individual, this active particles has a active orientation in which they are supposed to move, and this orientation is Hattie, and particles actually have some velocity. So if this is completely overdamped, this velocity, this active velocity and this orientation, they should be aligned. So this misalignment between them, so that remains up to some time scale, and this is the time scale over which it remains, and that shows this delay between these two functions. If there is no delay, these two quantities, of course, like if these were like equilibrium quantities, this should have been 0. So I am taking 2-point correlation between velocity and orientation, but this is, if this is in time t, this is in minus t. So subtracting these two out. Okay, so this says that there could be important impact on of inertia on the dynamics of these active particles, but then if one goes back to the scenario of MIPS, motility induced phase separation, this was shown by Hartmut-Lowen's group. So what happens is that if you have this inertia, this capital M quantity here, this is the ratio of the inertial relaxation time by the persistence time. So this ratio, this one, inertial relaxation time by persistence time. So if this ratio becomes, unless it's too small means this is like 7%, unless it's not less than 7%, you can't see motility induced phase separation. For any larger ratio of this inertial time scale, motility induced phase separation completely disappears. So it's a many-body effect. So a phase which disappears and presence or absence of the phase depends on inertia. This behavior is of course like very unlike of whatever we know from our equilibrium physics. So in equilibrium physics, of course, all the late time properties don't depend on inertia. So there, for example, even this thermodynamic properties, temperature, pressure, chemical potential, they are not inertia dependent. And even kinetic quantities like kinetic temperature, Tackt particle diffusivity, mobility, these quantities, asymptotic properties of them, they are independent of inertia in equilibrium systems. And of course, equilibrium phase transition does not depend on the inertial part of the Hamiltonian, this just depends on the interaction. And one just looks at the partition function from the interaction part and describes the phase transitions. So I have already shown in this active system one example that MIPS gets modified in presence of inertia. What we'll try to do in this talk is to show that what are the other possible impacts of inertia on active processes. So how these equilibrium notions are violated in active matter. Okay, so with that I come to the outline of my talk. So what I try to do is that, so this is the basic question, that how particle mass affects late time or steady state properties of active systems. That's what we will try to probe. And for that first example, I will show active polymers, properties of active semi-flexible polymers, and I will show that in presence of inertia there is a re-entrance towards equilibrium-like properties. And in active Brownian particles, as I already mentioned, that this MIPS, Hartmut-Lowen's group showed that MIPS disappears if you have little bit of inertia, only 7% with respect to persistence. So I would like to ask this question, that what happens to other steady state properties even if I don't encounter phase separation. So if I keep my activity low enough, my density low enough, so that I don't encounter I showed in that phase diagram that there is a regime of motility induced phase separation. Below that there is a homogeneous isotropic kind of phase. So even in that phase, is there an impact on the Tackt particle dynamics of this system? And finally, we'll do some exact calculations in using ideal system of inertial active Brownian particles. Maybe I should call this active Langevin particles. Okay, so the first example. So this first example of active semi-flexible polymers was, so I'm just giving again like the overdamped motivation, active semi-flexible polymers, people have been looking at it from, for example, from the perspective of understanding biological systems. Here there is this experiment done on actin filaments on myosin bed. So these are myosin molecular motors coat the once this substrate on which this glass cover slip, and the actin filaments are being driven by this irreversibly attached myosin motors on the substrate. As a result, actin filaments are driven on top of it. And this was shown long back that these actin filaments undergo this instability and gets into this spiral formation, spiral dynamics on top of this molecular motor assay. So, motivated by that, there are several studies, and our group also had looked at such systems. So, in which one can model the length stabilized actin filaments as semi-flexible filament. So, I will not get into the full detail of this model, but these are like bit spring models in which semi-flexibility is incorporated by giving a bending rigidity between consecutive bonds. And then there is an active force. Molecular motors try to work on top of this actin filament, and as a result drives it in the opposite direction but tangentially. So that can be roughly modeled as a local tangential active force acting on top of this filament. And if you increase this active force beyond a point, you see this buckling instability, that the head of this filament can buckle, and after it buckles, that gets into a trap and gets into this spiral formation, and the lifetime of this spiral depends on the length of the filament. So if one increases the length, the spiral remains in the spiral phase for a very long time, and after some point, of course, it can come out of that spiral, and because there is no chiral symmetry breaking, it can go either right-handed or left-handed spiral, but it keeps on jumping between one to the other. So that happens at in the overdamped limit itself. So then we are interested to see that, okay, so one can also imagine developing this similar semi-flexible chain of active elements, but in more macroscopic, more granular matter scale of systems. So maybe one can also head to tail connect various hex bugs together and make a filament out of it and look at the dynamics of this. So what will happen in such a system? So what we see is that some behavior which is sort of reminiscent of that motility-induced phase separation, disappearance of motility-induced phase separation with inertia that Hartmut-Lewin had seen. What we find here is that, of course, if inertia, I can ignore inertia, that was the previous work. In that limit, with increasing Peclet, with increasing activity, there is this buckling instability that's encountered, and the system gets into a spiral, spinning spiral state. So I am calling it a spinning active spiral state. So it goes into that. But if you increase inertia, then you can see that beyond a point, what happens is that if inertia is large enough, this will not get into that phase, and you see that this phase, the spinning active spiral phase, that region that decreases, that size of that region decreases as I increase inertia, and at large enough inertia you see this reentrant transition, that if you increase activity here, of course first you will encounter this buckling instability, you will get into this spiral, and at large enough inertia this spiral again becomes unstable towards the open chain. So that's what happens. So I quickly show you, yeah, so no, it's always there. Okay, so for example, so it's always there, but it's a question that how long it can spend in the spiral state. So that time scale, how long it spends in the spiral state, that decreases. So what happens is that if you look at the probability distribution of how much time it spends in the spiral state and how much time it spiral state right-handed, left-handed, and how much time it spends in the open state. So this distribution will have 3 maxima, and the weight of this maxima increases and decreases. So that's what happens. So I don't think I am showing it here. Yeah, I skipped that for the sake of time. But that's what happens, that here open chain is more predominant. It's not that it will not get into the spirals, it will get into the spiral, the probabilities are pretty low. And in this region, the probability of spirals are high, and the open chain is, that probability is very low. So it, even at m equal to 0, it also of course goes through open chain from right-handed spiral to left-handed spiral. Maybe interesting is this lower one. The spiral forms because of the buckling instability, but how the spiral breaks, is that suddenly this innermost region that turns back, and that turning back, the probability of that turning back increases as one has inertia and inertial collision, which makes a space, and after collision, if it comes out and makes enough, large enough space by which before it goes back, the persistence, the knowledge of persistence is lost, so it cannot go back exactly there, it goes back somewhere else. That's how you can break these spirals and lower the probability of these spirals. If you make the particle soft, yeah, so if you make the particle soft, that will increase the probability of the spiral, but that will just shift the boundary. Yeah. Okay, so then the other thing, let me just quickly just concentrate on this quantity. This is a Kullback-Leibler divergence between the end-to-end probability distribution of the equilibrium chain and the non-equilibrium chain in presence of this activity and inertia. So if you look at this quantity, what you see is that as a function of Peclet, so smallest inertia it increases, it shows some fluctuations here, but for the largest inertia values that I have shown here, you see that it increases, shows a maximum, and then comes back. It's suggesting that at large, in the presence of large inertia, equilibrium like behavior returns at large enough Peclet. So small intermediate Peclet, it becomes driven out of equilibrium, and then in presence of inertia, it becomes equilibrium like at large enough Peclet. So we'll encounter this feature several times. So how much time I have? 10 minutes? Okay. 10 minutes before 15 minutes. Okay, fine. So to summarize this part, that we have shown that active spirals destabilizes due to inertia, and at high inertia, activated equilibration like behavior we see in the presence of larger Peclet. So we'll try to understand this. This behavior we'll see in other contexts as well. So this was the work done by Chitrak and in collaboration with Abhishek, who is in ISAR Mohalik. Okay, so then let me go into active Brownian particles. The first look at the simpler parts. So simpler system is that okay, so I can just think about a single active Brownian particle, ideal case, and then I can think about active Brownian particle in a harmonic trap. So we'll analyze this two, because for this two we can do exact analytical calculations. So how do we go about it? So if this is the simplest idea, that the overdamped system, we are writing that in presence of, so what is happening, that there is a position, the position gets updated because of this active force, and the active force along certain heading direction, that's hat u, and there could be thermal noise on top of this, there could be some potential, but this orientation gets randomized. So as a function of time, so this orientation undergoes a rotational diffusion, and that rotational diffusion gives rise to this persistent motion of these particles. So in 2D you can write it in this way. That was the overdamped thing. Simplest way to make it underdamped is that I'll use theta dot equal to some angular velocity and look at the dynamics of the angular velocity in presence of dissipation and fluctuation. And similarly for the in the presence of translational inertia, we'll do the same thing. Let's look at the velocity and evolution of the velocity. That's simple stuff. And okay, so the whole equations we can write down in terms of using these two characteristic scales, the persistence time scale and this length scale L, which gives you sort of the length scale over which the particle can diffuse due to thermal noise uh, during the persistence time. So that's the length scale. So setting that these two together, you will get these four equations. So two equations for translation, two equations for rotation. So this can be in general present, but first let's take this perspective that we'll just look at the inertial effect in the translation, and rotation I'll say that this is, since it's an active process, rotation is an internal process in which I'm deciding in which direction I'll go, and that may not depend on my inertia. So total body mass, maybe I reduce my body mass by 10 kg, but I can still make the same decisions. So I can ignore this part and just keep this theta dot as equal to omega and look at this this reduced set of equations and analyze it. So in presence of J, things becomes a little more complicated. If time permits, I can show you what it is, or after the talk if anybody is interested. So with this perspective, one can write down these equations in general d dimension. So I can think about the motion of the particles in d dimension, and orientational dynamics happens in some other n dimension, and n can be equal to d or can be something else. So you can write down these equations. These are the Langevin equations, and of course straightforward to write down the corresponding Fokker-Planck equations, but it's not easy to solve these equations directly, the Fokker-Planck equations and the probability distributions directly. But what transpires is that it becomes easy that if we try to calculate the moments of the dynamics. So for that we perform a Laplace transform of these equations. This is the equation, and then write down an equation for a generic moment. So I say that psi is a function of all the dynamical variables, position, velocity, and the heading direction, and then you put this psi and can write down this generic equation for the moment. So this is the moment generator in that sense, and then one can go ahead and try to calculate particular moments for particular quantities of interest. Of course, for this system, quantities of interest are like velocity and velocity moments, position and position moments. So let me just quickly show at least one such calculation, how to go about it. So let's say that I want to calculate the second moment of velocity, so which will give me the kinetic temperature, for example. So to do that, one can set this psi variable equal to v square, and then I will also require a psi variable for the projection of velocity along the heading direction. So these two quantities, I put them back in the equation. So I'll get two equations and then solve these two equations together. So I'll get an equation for the velocity squared in Laplace space and this projected velocity along the heading direction in Laplace space. So these are these two equations, and note that both these equations have this generic structure. Their S dependence always comes in the form of 1 by S plus something and multiplication of those. So as a result, their Laplace transform will come out to be just exponential functions, and addition of exponentials, and what exponential, that they will give rise to the time scales, particular time scales of decay of these modes. So this same method works for higher order moments, for example v to the 4 etc., and position and orientation, everything. So that's number 1 point to note, and the number 2 point to note is the steady state is particularly becomes easy to calculate if I look at a quantity which has a steady state. For example, velocity will have a steady state for this free particle. For a particle in a harmonic trap, both velocity and position will get a steady state. So for them, one can calculate the steady state quantities, but just calculating the Laplace transform, multiplying it by S and going to S tends to 0 limit. Okay, so going ahead, so I can, of course, simplest quantities will be the orientational correlation which we expect. This is a persistent random motion, so should show a exponential with the persistence time. So I have already used the time in the units of persistence time. So this quantity says that within a persistence time this will decay, the orientational correlation. So then one can do this for velocity, do this for velocity projection, and then come back to this lag function that I had shown that in studied in this earlier experiment. So you can calculate that lag function, you get a closed form expression for that lag function, and which shows the same qualitative features. So we did not try to fit anything with here, so it just showed that, showing that they have the same qualitative features. So this lag function starts with 0 and goes back to 0 beyond the time scale. Okay, so so similarly you can calculate second moment of velocity, fourth moment of velocity, etc., and look at all the crossovers and crossover times. Everything can be analyzed. So and all these higher order moments in velocities, and so I'll not also stop there. Yeah, so the first interesting quantity in this calculation is the kurtosis of velocity. So if I look at this kurtosis of velocity, what one gets this exact calculation, and this exact form is plotted here. This is the heat map of this form, and this is a function of both this scaled inertia and Peclet number. So what you see is that in this form there are like this yellow regime is close to 0. Close to 0 means Gaussian like behavior of the velocity distribution, and corresponding distribution looks like that in 2D. And this region is where the kurtosis is strongly negative. Corresponding to that, the probability distribution looks like that. So it's a ring like probability distribution. What you see is that here, with increasing inertia at a given Peclet, you see a re-entrant transition, that you increase inertia. First you enter into this non-equilibrium regime, then you again come back towards this Gaussian regime. So one can try to understand how it happens. Crossover, re-entrant crossover. How do you understand this crossover? The first thing is simple, that if I look at this m much greater than 1, this regime, in that regime what happens is that the persistence time, so m much greater than 1 means that the persistence time is much smaller than the inertial relaxation time. So by the time the particle forgets its inertia, it already has forgotten its persistence orientation. So it becomes equilibrium like. 5 minutes to complete. Oops. So 5 minutes for question. Okay, fine. So this then what happens is that that's the simplest equilibrium like behavior. So below that, if you come below that, what happens at the near m equal to 1, you enter this region in which these two timescales compete with each other, and below, as I go m less than 1, in that regime, of course, my persistence is dominant with respect to inertia, and because of that I get this distribution which looks like this guy, with the peak of the distribution at given by the Peclet number one supplies. Okay, so that's understandable, but what happens below that? So in this regime where you see that this is becoming further it's becoming Gaussian, that's the regime in which in the presence of that activity, you are decreasing m, and this size decreases, and then beyond this point what happens is that the velocity fluctuation due to the thermal noise, that starts to dominate with respect to the velocity fluctuation. So as a result, you again go back to this Gaussian regime. So that's what happens here. So this is the cause of this reentrant transition. Okay, so I'll not say anything about that. Okay, so let me come to the steady state properties. So if you calculate the kinetic temperature of this system, you get this inertia dependence of the kinetic temperature. Effective diffusivity becomes independent of inertia. The swim pressure again depends on inertia and decreases with inertia. Kinetic temperature, you notice that it increases with inertia to saturate. Swim pressure decreases with inertia to vanish if inertia becomes really large. And the entropy production rate in the system, that also decreases with inertia. And final quantity we looked at is the violation of the equilibrium fluctuation dissipation, just looking at the effective diffusivity and the kinetic temperature, difference of that. So that quantity turns out to depend on this entropy production rate. So this violation depend. So it's understandable, we would expect that the violation of equilibrium fluctuation dissipation should be connected to the entropy production in the system. So depends on this non-equilibrium entropy production. But this note that the non-equilibrium entropy production itself that decreases as a function of inertia. So this is again the same statement that I was making, that with larger inertia, activity sort of makes thing equilibrium like. So inertial equilibration kind of behavior. A large enough inertia will get equilibrium like behavior. So sort of inertia dominates and activity fails to keep up to the inertial time scale. Okay, so I'll not look at this trapped thing. Jump. So jump to the many body effects. So this part, this trapped thing part, these two things were done by Manish, and Manish has a poster. If anyone is interested, you can go to his poster. So then this last part was that active Brownian fluid at a density and activity, so that the system does not encounter the motility induced phase separation. So even in that level, what happens? What happens is that we can then calculate certain things. The velocity distribution, etc., has certain interesting feature. One thing one can look at is that interesting thing is that if I sit on top of an active particle and ask a question, what is the local environment? So this depends on which direction the active particle goes into. So environment in front and back are different. So there is more accumulation of particles in front than in the back. So this asymmetry is there for the overdamped regime. As you increase inertia, the amount of asymmetry itself decreases. So sort of, and the reason being that there is a collision from front and then there is a back collision. So it comes back, this collision and coming back, that feature was not available in the overdamped regime. So that's what is something which can sort of try to equilibrate the system. And another feature, interesting feature I would like you to note is that the effective diffusivity in this system in presence of interaction, that guy depends on inertia. So we know that so overdamped limit, what we expect the effective diffusivity should scale as Peclet square. So that's the scaling we get at small inertia level. But as one increases inertia, this exponent, or at least the apparent exponent, that decreases and decreases towards almost like linear regime. So that's one thing. So this exponent alpha d, that depends on inertia, and as I increase inertia, it starts from the quadratic to almost linear. That's one observation. The other observation is that if I just fix the Peclet and look at the effective diffusivity as a function of inertia, so this guy decreases with inertia. So this property can be understood in terms of, so there is a argument that goes in. So if I look at particles in harmonic trap, there is a harmonic interaction, and in presence of harmonic interaction, even if I think about particles which are interacting with each other in a harmonic way, so particle can, if it collides with another particle, because the interaction is harmonic, it will penetrate that harmonic potential and stay a very long time. After that, it can come out. But if the interaction is hardcore like, so what happens is that if I increase inertia in such a system, it will spend more and more time at collision. But if I think about hardcore like interaction, what happens is that this guy at interaction spends very less time. As I increase inertia, it recoils and spends, like the time scale is extremely small. So these are this inverse of this time scale that gets into here. and with increasing inertia, since this guy increases, so as a result the diffusivity decreases. But there is no completely analytic theory for that yet. And so in this system also, like, we calculated the departure from the equilibrium fluctuation dissipation, which shows decrease as a function of inertia. Again, for this many body system, we don't have a exact calculation like in the single particle, but this is the feature which sort of agrees with the behavior we have seen for at least the single particle level calculations. So this calculation was done by Shubhendu in collaboration with Fernando. So in this talk, what I tried to show is that unlike in equilibrium, inertia impacts not only the transient behavior, it impacts late time properties, and if the system can come to steady state in certain variables, the steady state properties depend on inertia. So one cannot just ignore inertia. And we have shown this dependence of inertial dependence of kinetic temperature, swim pressure, entropy production, diffusivity, and mobility. I did not spend time on that, and obtained several exact expressions. So basically, the take-home message is that inertia brings back equilibrium-like behavior. So thank you.
Yeah, hi. So I was just thinking about the first part of your talk, this active polymers like doing the spiraling. So you are saying that like it's a kind of initiated by the buckling. From a mechanical perspective, like buckling is like mediated by the mechanical stresses and modulus. So can I think about an analog like does this curvature or something scales with the activity in the system and so how does it scale?
So there is this activity in the system. You are actively driving the system. Actively driving the system means that tangentially you are driving. If everything was like on line, then all the forces you can balance by something. But these guys can dynamically, it can be in different orientations. So let's say this is in this orientation. So this part of this bond will try to move in that direction. This part of the bond will try to move in that direction. These two will generate an instability that this bond initially was this can increase the bond angle, right? So that's how the instability gets into the problem. So locally, that's what happens.
I was just thinking, I understand how the instability is coming up. So, does this also scale with, the kind of activity you're putting in to the particles?
Yeah. So,
for instance, does the curvature
yes.
changes?
Yeah. So I'll show you. So, this is the balance. So this gives rise to a torque, and then you have this bending rigidity of this guy. So that's the internal and external torque balance. That's what happens, and as a result, you get this nice scaling that R square goes as 1 by F.
Is your activity that you're imagining of a relative from the spirals being like vibrated, or are you thinking you attend? Because the vibrated canalizations have been done by Arsha. There are lots of experiments by Arsha.
Yeah, so you can do it by vibrating as well. Only thing you require is that what we had been doing, that self I have not seen but I have not seen the same flexible filaments. Flexible filaments I have seen, of course.
How do you control that?
It should be easy. Like I mean, you can just. I was thinking about this.
Completely flexible.
No, I mean you can always like put a hinge and can give some rigidity to the hinge. That's it.
But I'm saying any canalization design
Will be some. Yeah, will have some semi flexibility, but if you can control that, then probably many of these features can be reproduced.
So you say just by controlling the vibration,
This other thing I am pretty sure is easy to control. Should not be difficult. And these are hinges.
But I'm saying, have you looked at the experiments?
I've tried to look up, but I did not encounter anything. So if something comes to your you know something, suggest me. It will be very helpful.